Hey, Matt287 folks. What we're going to be looking at today is we're looking at population models and separable equations. And these growth models are some of the canonical models for differential equations, right? They're basically like how fast, they want to tell us what's going to happen to a population. They want us to model a population based upon how fast that population is in fact growing, right? And so we'll start out with this idea of the Malthusian growth model. The Malthusian growth model is a model for growth where there are no limitations on the growth of the population. So the growth in this case is dependent only on the previous population, or the population at a time t. So we have a p of t, that's our population at time t, and then t is our time. And so we have dp dt equals kp, and what we're going to notice here is that this is fully separable. So we're going to use separation of variables because I can pull the p's over to one side and pull the t's over to the other side. So what that gives me is dp over p is going to equal k dt. And now that I have it in that form where my variables are in fact separated, I can take the integral of both sides, dp over p, is equal to the integral of k dt. And so consequently, what we get is we get the natural log of p is going to equal kt plus c. And what we want to notice is that in this case, it's a population, so it's never going to be negative. We don't actually have to utilize the absolute value here. We can just make this natural log of p equals kt plus c. Okay. And then what we're given then is that p, using our natural logarithms, p is going to equal e to the kt plus c, which is equal to ce to the kt. So the Malthusian growth model is an exponential growth model, right, where our rate of growth is this value k. In fact, any differential equation, right, basically where we're going to take a constant multiplied by our dependent variable is going to end up being one of these exponential growth models, okay? So in this case, we might look at it like the growth of a bacterial culture or the growth of something else. In this case, though, what you want to notice is that there's nothing that's actually restricting the growth of the population, right? So if k is greater than 1, the population is going to grow infinitely. Excuse me, actually if k is in fact greater than 0, will grow infinitely, all right? And we're going to take a look at that versus one where we see some limitations that are actually going to happen on the population growth. So in the Malthusian model, what we'll do is we'll replace c in p of t equals ce to the kt with p naught, the initial population at time t0. So what that'll give me is that p of t is then going to equal p naught e to the kt, where p naught is my initial population and k is the rate of growth for my population. So let's look at a problem using the Malthusian model. So the number of bacteria in a certain culture will grow at a rate that is proportional to the number present. If the number increased from 500 to 2,000 in 2 hours, we want to determine the number present after 12 hours and also the doubling time. And so the doubling time is how fast does it take for the number in the population to double. And we'll look at a really easy way to go about doing that. So our model is going to be p of t equals p naught e to the kt. And p naught in this case we know is going to equal 500 because that's the initial population. And p of 2 is going to equal 2,000. So we're going to utilize that information. We're going to plug in our relevant information in order to first solve for k and then get a function that we can use then in order to solve these problems. So p of t is going to equal then 500 e to the e to the kt. And so that'll mean that p of 2, which equals 2,000, will equal 500 e to the k times 2. So what we get now is we get that, moving down this way, 400, or 4, will equal e to the 2k. And that'll mean that the natural log of 4 will equal 2k. And so consequently k equals the natural log of 4 over 2. Okay, let's just keep that way and then write out our function. So that means that p of t is going to equal 500 e to the natural log of 4 over 2t. And we'll use that then in order to solve our two problems. Let's start with number 1. So number 1 is the number present after 12 hours. So this is going to be p of t or P of 12 rather, is going to equal 500 e to the natural log 4 over 2 times 6, which ends up equaling 500 e to the 3 ln 4. Now we'll plug that into our calculator in order to figure out what that is. What we get then is we get that P of 12 is going to equal 32,000 bacteria. For our second one, we're basically going to set our number, the doubling time now for this one, is we want to know at what point in time is the number of bacteria going to end up equaling 1,000. So 1,000, right, which is double of 500. So 500 is the initial population. 1,000 is how many we have once we've doubled. So 1,000 is going to equal 500 e to the ln of 4 over 2 t. Okay, so that gives me then 2 is going to equal e to the ln 4 over 2t. So that will tell me then that ln of 2 will equal natural log of 4 divided by 2t. Okay. So then this gives me then 2 ln 2 equals ln 4t. And in fact, you can actually see that this is in fact ln of 4, because this is going to end up being ln 2 squared is going to equal ln 4t. And so consequently, t is going to end up equaling the natural log of 4 over the natural log of 4. And so t equals 1 hour. So our doubling time here is going to end up being 1 hour. That's probably the simplest way to go about doing doubling time. There are equations. You can look up the equation in the book. But I think it's important to kind of understand when we say a doubling time or finding a half-life, that it's basically just taking that initial population and then either doubling it or cutting it in half. Okay? So that kind of demonstrates how it is that we utilize the Malthusian model and we do problems utilizing the Malthusian model. Okay?